Hello everyone. It's time for a Signals and Systems example. Today's topic is convolution, and we're going to see an example of convolving two continuous time signals. So let's get started. Okay, so the convolution integral, as you hopefully remember from class, looks like this. Y of t, the output of the convolution, is equal to the integral from minus infinity to plus infinity of x of tau times h of t minus tau d tau. So x and h are two given functions. And so for this particular example, I've defined x to look like this. It's a little square pulse that's equal to 1. I guess I should mark that on there. It's equal to 1 between 0 and 1, and it's equal to minus 1 from 1 to 2. And then h of t looks like this signal here. It's equal to minus 1 from minus 2 to minus 1, and then it's equal to 1 from minus 1 to 0. Okay, so what you notice right off the bat is that actually h of t for this particular example is just the time-reversed version of x of t. Okay, so in order to implement the convolution integral here, we have to be able to sketch these functions as a function of tau. So we need x of tau and we need h of tau first. And we can easily get those. We basically have the sketches already. All we have to do is replace t in these sketches by tau. So everywhere we saw t, now we replace that with tau. Okay, so I've done it for x. Now let me do it for h, just erasing the t and replacing it with tau. Okay, all right. I guess I could make that tau a little bit clearer. So that's what we have. All right, so now we not only need h of tau, we need h of t minus tau. So the first step, as we know from class, to getting h of t minus tau is to first sketch h of minus tau. So just sketch the time-reversed version of h. Well, that's pretty easy to come up with. So I'll just sketch it here. I just flip h about the axis, and that actually gets me exactly the signal that looks the same as x for this particular example. So I have this h of minus tau here. I've just time reversed the h of tau. Okay, now what I really need in this integral is h of t minus tau. Well, that is just a shifted version of h of minus tau, where I've taken the origin, so the origin of the h of minus tau graph, and shifted it to t. So let me sketch it over to the left here. So I'm going to sketch h of t minus tau, and I'm just going to do it for a particular value that I choose of t. So here is h of t minus tau. Now what was at the origin right here in this graph will be at t in this graph. So this is t plus 1, and this point is t plus 2. I haven't changed the amplitude at all. And this is a plot of h of t minus tau. So all I've done is take this graph here and shift it so that the origin of this graph now is at t. And t is an arbitrary parameter in this case. So t, just as I change the value of t, this graph shifts up and down this axis here. And we have to calculate the convolution output, the y of t, for all possible values of t. Okay, so typically we do this. The first thing that we do after we've done this sketch and this sketch is we identify regions for this convolution, because regions are where this multiplication has, that I multiply x of tau times h of t minus tau has a unique form. because I do the multiplication first and then I do the integration. Okay, so if you're doing this at home on your own, I recommend you pause the video now and try and figure out how many possible regions there are. So take a minute and pause. Okay, so hopefully you have figured out for yourself how many regions there are. I have done that calculation for myself, and what I've sketched here is region 1. Okay, so in region 1, now for all of these graphs, I'm going to, the sketch of the black curve is always going to be the sketch of x of tau, and now the red curve, just draw this on here. The red curve is always going to be h of t minus tau. Okay, so I've sketched them on the same graph so that I have them together. Okay, so now this region, I've sketched it as if this region is defined by t plus 2 being less than 0, right? There's no overlap in these curves. And that will be true so long as t plus 2 is less than 0, or t is less than minus 2. So region 1 is the region where t is less than minus 2. And in this case, I can do the sketch again. Remember, I'm trying to multiply these two signals. I'm multiplying x of tau times h of t minus tau. And if I do that multiplication, and I sketch the result here, I just get 0, because everywhere h is non-zero, x is 0, and everywhere x is non-zero, h is 0. So I just get 0 out. This will be 0 everywhere. And so in this region, y of t is the integral of 0, or 0. So in this region, the output is equal to 0. So that's pretty easy to figure out. Now if we look at what happens when we start sliding this guy to the right, well, what will happen is that eventually this edge will get to be greater than 0, and then we will have some non-zero overlap. So this next page shows you what happens for that case. So in this case, this is for the region where now we've shown the right edge here of the red curve is where t plus 2 is, and that's now greater than 0. So this region is defined by t plus 2 being greater than or equal to 0, but a key thing here is this edge here hasn't yet hit 0. So this region is defined by t plus 2 greater than or equal to 0 and t plus 1 less than 0, or t is less than minus 1, and t is greater than minus 2. So the region is really t between minus 2 and minus 1. So that's what region 2 is. And in region 2 now I have to sketch the signals x of tau times h of t minus tau. Actually, let me just redraw this so that I really remember showing you h of t minus tau is in red. So now it says I have to multiply these two things together. And if I multiply those two things together, I get this curve. So I'm going to multiply these two. Everywhere in this region here, I'm going to get 0 because I'm multiplying something non-zero by exactly 0. It's only in this region here between 0 and t plus 2 that I'm going to get anything. And in that region, I get, so this is 0, and this is t plus 2. In that little region, I get something that's equal to minus 1. Because what I have is 1 here times a minus 1. 1 times minus 1 is minus 1. That will be true for every point in this region. Okay, so that's what my sketch of x of tau times h of t minus tau is equal to. And remember, y of t is just the integral of x of tau, h of t minus tau, d tau. Well, the integral is just the area. Well, the area under here will be, we're just integrating actually from minus infinity to plus infinity, but the only non-zero piece is from 0 to t plus 2. So it'll be minus 1 d tau, because that's what the function is equal to, between 0 and t plus 2. And that's just minus tau evaluated between 0 and t plus 2. And if we evaluate that, the final result is going to be minus t minus 2. Okay, so in this region, I'm just going to summarize it up here. In this region, y of t is equal to minus t minus 2 in region 2. Okay, and we get that because we've multiplied these two functions together and now we've integrated them. Okay, so that's region 2. Now the next region will be, we will find the next region. We're going to keep sliding this signal to the right and we'll find the next region. Alright, so here's region 3. I've sketched what region 3 should look like. And what is this region defined by? What are the intervals? Well, in this interval, what we've shown is we've slid it a little farther to the right, and now we know that t plus 1 is bigger than 0. Okay, so now this is inside here. And t plus 2 now has moved outside of 1, right? So it's moved to the right of 1. And so we can summarize what this region is. This region occurs when t plus 1 is greater than 0 and t plus 2 is greater than 1. So that'll be t is going to be between minus 1 so t plus 1 is greater than 0. So let me summarize that one first. So t is greater than minus 1. And t plus 2, the right edge, is greater than 1. So t plus 2 is greater than 1, which is the same condition here, but also t plus 2 is less than 2. So t is less than 0. So the condition for this particular region here is, and let me summarize this a little bit better. I'm going to erase this here. So I didn't say that all that clearly. So the condition is that t plus 1 is greater than 0, t is greater than minus 1, and t plus 2 is still less than 2, right? Because we haven't hit this edge over here. So t is less than 0. So this is for the region for t between minus 1 and 0. That's what region 3 is. Okay, so in this region, we have to multiply these two signals together. So we're going to calculate x of tau times h of t minus tau. Okay, so I'm just going to do the multiplication of these signals and sketch the result. Okay, so now if I'm multiplying these signals together, what am I going to get? Again, the result is a function of tau. Well, in this particular region here, it will be 0, because only h of t minus tau is non-zero, x of tau is 0. In this region here, we'll have something non-zero. In this region here, we'll have something non-zero. And then we'll have something non-zero here, and then 0 here. So let's sketch what this is going to look like. So at 0, it will be equal to 1 times 1. Oops, got to change it back to the pen. At 0, it will equal 1 times 1. and then it will go down here. It will equal 1 times minus 1, so it'll go down. And then and it'll go over. And then here, right, it'll turn into minus 1 times minus 1, which is positive 1. So it'll pop up to positive 1, and then it'll go back down to 0. And so I have to mark the edges here. And so this edge here is going to be at, this edge here is at t plus 1. And this edge here is at 1, and this edge here is at t plus 2. Okay, so that's what we have. This is 1, this is minus 1. And so we have to now integrate to get the area under the curve. So now we're going to actually have 3 different integrals that we're doing, right? Because in this region it's equal to 1, in this region it's equal to minus 1, in this region it's equal to 1. And so let me see if I can fit this integration down here at the bottom. So this is for region 3. So y of t is going to be equal to, well, it'll be equal to the integral of 1 d tau between 0 and t plus 1, plus the integral of minus 1 d tau, that's in here, from t plus 1 to 1. So that goes from t plus 1, whoops, running out of room on my screen here. It goes from t plus 1 to 1, and then plus the integral from 1 to t plus 2 of 1 d tau, because it's equal to 1 in here. Okay, so now I can easily calculate the results of each of these integrals. Now it's quite easy to calculate each of these integrals individually, because the integral of 1 d tau is just tau. The integral of minus 1 d tau is just minus 1. So then all it is evaluating between these various limits. So that's straightforward to do. And so if I do that, I get for the first integral here, for this one, the result is equal to t plus 1. For the second integral here, what I get, the result is minus 1 minus t minus 1. And then for the third integral, I get plus t plus 1 minus 1. T plus 2, sorry, minus 1. Okay, and so then I can add all those together, and if I do that, my overall result is y of t is equal to t plus 1 minus 1 minus t minus 1 plus t plus 2 minus 1, and that will be equal to, let's see, the t's, it'll be t plus t plus t, that'll be 3t, and then it'll be 1 plus 1, sorry, 1 minus 1 plus 1, alright, so it's just 1 plus 2 minus 1, so that's plus 2. So the result in this is 3t plus 2. Okay, so that's for region 3. Now we move over to region 4, and here's the sketch for region 4. Hopefully it gets a little easier even now. We can easily specify what this region is. Region 4 is where t plus 2 now is greater than 2. T plus 2 is greater than 2 because we've moved outside here. So that means t is greater than 0. And yet t plus 1 is still less than 2, so that we're still in there. And t plus 1 is less than 2. So t is between 0 and 1. Whoops. T is between 0 and 1. So that is the next region. Okay, that's the next region. And now we just do the sketch again. So now I'm going to sketch x of tau times h of t minus tau. So I'm sketching the result of that. And here's my sketch of the result. So now we have, in this region it's non-zero, and in this region it's non-zero, right? And so here's what my sketch is going to look like. So it's going to go up at t, whoops, and then it'll be equal to minus 1 from t, so it starts at t, it goes down at 1, comes back up at t plus 1, whoops, comes back up all the way at t plus 1. That's at t plus 1, and then the right edge is at 2. Okay? So, all right, that's just multiplying these two signals together point by point. And that's 1, and that's minus 1. So we can write out the integral. Again, it's pretty easy to do. The integral between t and 1 is 1 d tau. And the integral between 1 and t plus 1 is minus 1 d tau. And then the integral from t plus 1 to 2 is 1 d tau. And so this is, again, straightforward to evaluate. This will be equal to, whoops, need my eraser. This one will be equal to 1 minus t. This one will be equal to minus t plus 1 minus 1. And this integral will be equal to plus 2 minus quantity t plus 1. All right, so this is a minus t, minus t, minus t. So this will be minus 3t. And then this will be 1, that's 1 minus 1, so that's 0, plus 2, 3, which is equal to 3, and then minus 1. So this will be plus 2. So this is minus 3t plus 2. So in this region, y of t is equal to minus 3t plus 2. Okay, so we have region, now region 5. This is the integral that or the region 5. And so now in this region is defined, I've done the sketch here, but it's defined now. T is greater than 1. T is greater than 1, but t is also less than 2. Right? So t is between 1 and 2 in this region. And in this region, if I do the sketch of x of tau, and then multiply that by h of t minus tau, the resulting sketch that I get looks like this. So there's only one region here where they're both going to be non-zero at the same time, and that's right here in this region. And so it will be equal to, whoops, it will be equal to, in this region, 1 times a minus 1. So the result is minus 1, and that's from t to 2. So the integral in this region of x of tau times h of t minus tau is just the integral from t to 2 of minus 1 d tau, which is minus tau evaluated between t and 2, which will be equal to minus 2 minus t, or t minus 2. So in this region, y of t is equal to t minus 2. Then we just have one. So we have one region left to look at, and it's region 6. Region 6 now, in region 6, this is, remember, this edge is t, this is t plus 1, this is t plus 2. Now, region 6 is defined where, now there is no overlap of these, so t is greater than 2, greater than or equal to 2. That's region 6. And in this region, x of tau times h of t minus tau. If I do a sketch of that, I just get 0. It's 0 everywhere. And so y of t is equal to 0 in region 6. Okay, so this, we've done all 6 regions because this will stay the same no matter how big t gets. So if we now try and, here's what we have. So all I've done here is summarized what our function is equal to, the results we got in each of the 6 regions. And so now I'm going to sketch what it's equal to. So before t is minus 2, we're equal to 0. And for t greater than 2, we're equal to 0. So we know our function looks like that. Now, the first function that we have here in this region is minus t minus 2. And so what does that tell us? Well, it says we have a slope, a negative slope of minus 1, so it'll be going down. Slope of minus 1. The intercept would be at minus 2, so it's sloping down like this. But remember, this is only valid between minus 2 and minus 1. So let me sketch that in there. It will be, gotta get my pen working here. So it will look like this. Now, if that were valid over the whole region, then we would just continue this line. But it isn't, right? Because in region 3, which is between minus 1 and 0, it changes, right? And now it's equal to 3t plus 2. So that's a line sloping upward with a slope of 3, and it intersects the y-axis at 2. So what that line will be is it will go up like this, and it'll intersect it at 2. Okay? All right, and that, notice that it's equal to the same thing, right? At minus 1, this is equal to 3 times minus 1, which is minus 3, plus 2. So that's negative 1. So it starts off right there, and then it intersects the y-axis at 2. Now in region 4, we skip over here. Now, well, we have the same y-intercept, so we're starting at the same place. Now it has a negative slope, a slope of minus 3. So what we're going to see, this is just a line that goes down like this and hits minus 1 down here. So that at 1, right? At 1 it's equal to minus 3 plus 2, which is minus 1, which is down here. And then in this region, region 5, it's t minus 2, so that's an upward slope with a slope of 1, and it would intersect the y-axis down here at minus 2. So it's a line that goes like that. Okay, so this should look, ideally, this should look symmetric. My graph isn't all that great, but I think you get the general idea here. So this is an example of doing a slightly more complicated convolution, perhaps than we did in class, and hopefully it's been a useful example for you. So, just to summarize, let me, so we've done hopefully a good convolution example. I hope it will be useful to you, and you can check out these other links if you want more information about when this video was produced or for what class. So, hope you've enjoyed listening and that the example has been useful.